here's the Sap. And as I said, we start Sap from left to right and from up to down. So the first thing we get is file, and then from up you have a new model. That's the first thing we do, go to new model. And as you guys can see, all the units I have here is Kip's foot. So actually before I do that, I'm gonna go here, change the units. Gives you all kinds of units you can imagine, the kilograms, meters, newtons, tons. So we want Kip foot, so we go with the Kip foot. And you can change it anytime during the the analysis. So I go to File, New Model, and it's now Kip foot. And I want a grid only. That's the easiest way to do it, is to use the grid only option. So we go to grid only. If you click on grid only, gives you number of grid lines needed in X direction. So in X direction, I already defined that before anything. In X direction, I need only 3 grid lines. So I'm gonna put 3. Right, that's what we need, X1, X2, X3. So 3 grid lines. Then in Y direction, we don't care about the Y direction because we're doing 2D analysis, right? That's Y is the out of plane. So we don't need only 1 grid line. Can't put 0, it has to be 1 grid line because that's gonna be, you have a Y1 is this plane. That's the Y1. Then in the Z direction, we have 3 as well. So that's gonna be 3 in Z. And then it asks you what's the distance. So it specifies a constant, like a uniform spacing, the same constant spacing. So we can change that later. So I'm gonna keep it in X as 24 because that's what I need, and then I can change the other 1 to 6. I'll show you how I can edit the grid. So I keep it, I mean, these numbers don't mean anything. I can keep it like that. And then why we don't care what the number is because we have only 1 grid, so there's no spacing. Here it asks for grid spacing, right? So we don't care about the grid spacing. We have only 1, so any number will work. And then Z, I can leave it as 12. I mean, I'm gonna change that later. So that's not my problem with the space. I would have cared if I had a constant spacing, but here I don't have a constant, so I have to adjust it anyways. So, and then it asks where do you want to start the origin, so I want it at 0 too, not to confuse, but some people try to move it somewhere else and makes it confusing. I don't see any reason, to do that. To have this somewhere else doesn't make sense. So we click OK, and we don't need, you see it gives you 2 views, XY plane, and it gives you a 3D plane. The 3D we don't really care about, so we can just get rid of it. And here we need the XZ plane because we are analyzing an XZ. Right, so we need the XZ plane only. So you have here an option of going to the XZ view, and that's what we see. The grids, the spacing here is between X is 24, so you see that's 0, 0, that's 24, and that's, you guys can see the coordinates here at the bottom, it says here, it shows you where I'm at. So this point here is 48, which is 24 multiplied by 2, and then that's 12, Z is 12, and then Z is 24, and Y is going to be always 0 because we set it this way. So I can right click anywhere on the screen and go edit grid data. So I get the grid data, I click on modify, I want to modify it, so it gives me the grids. So actually SAP used, instead of X1, used grid A, B, and C. So that's just a name change. So all what I need to change is these numbers. I can change 48, which is X3 or C, change it to 30. And then for the Z, I need a grid at 6, and I need another one at 18, so I'll just put here 6 and 18. And then you click OK, and now you're gonna change, you see that changed the, how the system, how the grid lines look like. So that's the first thing we want to do, before anything else.
Yeah, I'm using a Mac, so it doesn't have a right.
Oh, really? Okay. So the other option you can do it is to double click on the grid line. If you double click like that, I don't use Mac, so I mean, there's another option. I mean, look at this option. If you click on, double click on any grid line, it's gonna show you the same thing. You don't have the total. So that's the grid. That's the first thing you want to do, and then you can save. Let's save it somewhere, like, for example, 1. So once you do that, as we said, we start left to right. So there's nothing here we need from the file other than new model. We don't need anything else. We just need to save it, and we did. Edit, we're not doing any edits, we're not doing any view stuff, so we need to define. Now we need to do some definitions to define, put some information. So you see the first thing we see is define materials. We need to make sure we're putting the right materials. So I click define materials. First of all, I'm using a W section, right? So when I'm using a W section, I need to go. I'm using a W section. I need to know what type of steel I'm using. So I go to table 2-4. Go to table 2-4. If I don't give you the material type, then you're gonna select the preferred material from table 2. We talked about table 2-4 before, right? We mentioned that's the. So we're using a W section. So which material should I use then? Yeah, so you go to this table for a W section. That's all the sections we have are W sections. So we go, since we didn't specify a type of material, then use the preferred one. And that's what I do in exams, even in homeworks. I don't tell you what material to use, so you have to go and select the preferred one. Unless I tell you, like I can tell you a W836, that's not the preferred type, but I needed a mild steel. So we use 830, but here, the preferred one is A992. So we're using A992. So we're using A992 steel, and that's Fy is equal to 50 KSI, and so that's the yield. F ultimate is 65. 65 KSI. So we have to make sure we're using the right material here. So Sap is very good software. It already has A992 for us. If we didn't have A992, then we would have to add a new material. Then we have to go there and add, and it has a library of materials. Like you can see, there's A36, 53, 500, 572, and then it doesn't cover all of the ASTM designations, so you can go and have a user specified one. But here we got A992 already, so we don't have to care. Just maybe we need to look at it. And as you can see, that's A992 grade 50. That's weight per unit volume. Maybe I need to change that to KSI. I can change that to KSI. So you see the elastic modulus of steel is 29,000 KSI. Poisson's ratio 0.3, and then that's thermal. We don't care about thermal. That's the shear modulus. We care more about the yield and ultimate. The expected, this stuff is for seismic, so we don't have to worry about it. So we care about the 50, 65, 29,000. That's the most important parameters. So it's already given. So I don't need to define a new material, because the material is already specified. So I just need to check and make sure it's correct. So I define the material, I need to define a section property. So as I said, we go from up to down. Section properties, we have frame sections. We don't have any tendons, we don't have any cables, we don't have any shell elements or solid elements. So only frame sections, so specify frame sections. And now we need to specify a W14 by 109, 21 by 44, 14 by 99. Yeah.
Did you switch it back to kids real quick, or you kept it PSI?
For what? What's that?
Well, you check to see if all the modules will be less because you went to PSI, right?
KSI. Yeah, 29,000 KSI.
Did you keep it like that?
Yeah, I mean, what I did is that I went to material and then changed the units here to KSI, and then 29,000 inches, right? And you can, if you want, we can do it Newton millimeters, but I don't want to put it. Right? I mean, it doesn't matter. I mean, it does the conversion for you, so you don't have to worry about any.
Where did you find A992?
Yeah, table, you remember this table we talked about, table 2-4? We said that has the preferred material type, right? For a W section, we use A992. For an angle, we use A36. The solid one is the preferred material type. It says here preferred material specification, and then the gray one means that it's not the preferred one, but it's available.
Sorry, Sap just started working for us, so could you tell us the grid lines you had set again?
They're here, right? That's the
okay.
ones, yeah.
Okay, cool. 3 on 3, 24.
But we will do some more steps, so you guys just, you can focus more on what even if you miss something, it's not a big deal. We'll do more steps. It's just give you the main idea here, so. So we need to put frame sections, right? So we go to sections, frame sections, and then we. So that's the thing. You have two options for frame sections. You got an option here. We have table 1-1 in the specifications. Tell you what the sections look like. Gives you all the information about the section. So if you have a W21 by 44, like this one, you see 21 by 44, then it can give you all information you need about the cross-sectional area, depth, thickness of the web, thickness of the flange. So that's the thickness of the web, that's the thickness of the flange. Gives you all information you need. You can input all these numbers manually. But SAP is too advanced that you can, instead of doing that, so you can do it, but it takes time. Instead of doing that, you can import a section property. So that's what I'm gonna do. I'm gonna go import. So if you click import a section property, it says here a steel section. So you have the option of concrete, aluminum, but we're interested in steel. So that's an I wide flange. That's what we need, a wide flange. A W section means a wide flange, I beam. Not interested in the rest. So click here. You see it opens a database where you can find all kinds of sections. So I use the AISC Pro database. Has all the sections. So if you scroll down, you'll find it here, and then you open. Find HP, you find M, S is the standard I-beam, and then you start finding the W sections here. So we need 3 sections. We need a W14 by 109, 14 by 99, 21 by 44. So I keep looking for these 3 sections here. So that's 14 by 99. I can click Control and select more than one if I want to. So 14 by 109 and then 21, here 21 by 44. So now I selected these 3 sections, and then I don't have to manually input any moment of inertias or thicknesses or anything like that. So
which 3 did you select?
the ones here, right? Because that's only the ones I need. These 3, right? I don't need all of them. I just need these 3. Because one column is a 14 by 109, one is 14 by 99, and then the beam is 21 by 44. So that's all what I need. If I had more sections, I would have selected more. So, yeah.
When you clicked on AISC,
Yeah.
which one did you click on?
The first one, not the 3 or, yeah, the first AI, the AIC.PRO.
Okay.
Yeah, that's the first one. The other ones are more like seismic and, code form. Have more sections I don't need, so I go with the simple. So I just click OK, and you'll see these sections now. These sections will show up here. So I have them. I just imported them. All what I did, I imported them from AISC. Got them here. So any questions so far? Is it straightforward, right? It's not. So also you have the option. I mean, let me go and change it to kip inches. I can do that in the middle. That's a good thing about SAP. I can keep changing the units as I need, and I don't do any conversions. So I want to go to kip inches and go back and look at these sections one more time. So if we look at 21 by 44, I selected modify, so show section. You see it gives me a height of 20.66. That's the height, width of the flange, 6.5, and so on. If you go to the manual here, you'll see 20.7, you'll see a 6.5. So it's the right numbers, right? Same thing as you see in the manual. So you don't have to input that. So it gives you, that's the dimensions, the thickness of the flange, thickness of the web, and so on. And also you can see section properties. If you click here at section properties, it will give you the area and cross section, the moment of inertia. It will give you all the information you need. So again, we can see that from the table. So the area was 13. See here 13. Moment of inertia about the x-axis. So that's x-axis. That's the moment of inertia. I. You go down here. That's 843 inches to the power 4, right? That's how we get the moment of inertia. So if we go, it's going to be moment of inertia is the same. 843. So all these numbers you can compare. Same thing. You do it for a 14 by 99 or 14 by 109, you get the same answer. Right. So, but that's in inches. That's why I changed the units into inches. When I just to look at inertias and areas in inches, because in square feet it's going to be completely different numbers because the AISC gives it in inches. So I had to go back. See, gives it in inches here. So I have to go back to inches. I can change that now, and I can change that now because I got the dimensions in foot. So I can change that now and go to kip foot instead. Go back to kip. See how you can go to kip foot and kip inches. Keep going back and forth. It's not a problem. So again, what I did pretty much is that I defined the grid lines. That's the first thing I did by new properties, put grid line, new model, and then I edit grid lines, and then I defined materials, made sure I got the right material A992, and then I got the sections. And you want to make sure that the sections, there is an option here in the section, it shows you the material used. So SAP already assigned A992, which is good. You don't want to assign 4,000 PSI, that's concrete, right? So you keep it steel. So you want to check that for all the sections you have, that it's assigned the right material for the right section. It's all A992 steel. So that's just some definitions, put here to define the sections, and then now I don't need a mass source. We need masses when we do dynamic analysis. When we have dynamic, because you're defining mass, when you have ground motions. Here we're doing earthquake as a point load. as a static load, so we're not doing dynamic, so we don't care about the mass. We don't care about joint constraints or all this stuff. We don't have functions, we're not doing, dynamic analysis again. So what we care about is loads. We want to assign loads. So we have so we assign loads. SAP already assigned the dead load for us. So we called it dead. The type is dead. So you have different types: dead, live, snow, whatever. And then you have something called a self-weight multiplier. That self-weight multiplier accounts for the weight of the steel section. So if you have a W21 by 44, it weighs 44 pounds per foot, per linear foot. So we mentioned in the example already that the self-weight is included already in so this 3 kip-foot includes self-weight. So we don't have to account for that twice. So we put the self-weight multiplier of 0. And then we click modify, you see a 0 here. That's what we want to do. So I'm not putting any loads now, I'm just defining the types of loads I have. So I have dead, and then I have a live load. So I'm gonna put live, and the type is live, and then add a new load panel, and then I have snow load, and the type here is snow, so I select snow and add, and then I have wind, and you have the wind option, and I have an earthquake. I just call it EQ, and here it's a quake load, and then you add. So I'm just doing some definitions. That's all what I do. As you can see, computers are not too smart. You have to tell the computer everything. So that's why we don't want to rely too much. You have to understand what the computer is doing, right? Like you have to know what's going on to input this stuff. You can't just, can't get anybody to do it for you. So I'm just,
Question.
yeah.
So did you change the dead load, the self-weight multiplier to 0?
0, yeah. Because it's included, right? And this distributed load includes the 44 pounds per foot. I already mentioned that. If it's not included, then I would have to keep it as 1. But now I don't want to account for self-weight twice. I already put it in the 3 kip per foot, and I don't want to have another self-weight. Because self-weight is a dead load, right? So you click OK, and that's the load. We don't want to define load cases or load combinations yet, so we'll keep that for later. And we just move on. There's nothing else on the list we need to do. Yeah, let's save that, so in case crashes or something, I don't have to do that. So we're done with this define tab. We go to the next one, draw. We need to draw, and we need to draw the frame elements. So I want to draw these elements: frame, cable, tendons. It's frame of cable, so it's frame. So I'm gonna click here, see the cursor changed, and then now we want to. We have node 1 to node 2. That's a frame element. And then you can right click on it and start again from here. And we have another element. Element 2 is the column. So that's from node 4, which is here, to node 3. And then I have from node 2 to node 3 another element. And then from node 3 to node 5. Right? And then that's it. You can just get rid of it.
So you always start with the vertical first and then
Yeah. I mean, we like, as I said, every element has a start node and end node. So if you look carefully how I drew that, I'm trying to draw everything from bottom to top. So I have all the start at the bottom, the end at the top. So that's what I'm trying to do to be consistent, to get good results, to get the sign conventions we are used to. But if you do it the other way around, it's just going to be confusing with sign conventions. So that's, and then everything from the beams, anything horizontal from left to right. So that would be the, the start is the bottom, end is the top. And then for horizontal, for beams, start is the left, end is right. So that's what I'm trying to do. So now I drew,
Why do you model the top beam as two separate?
Yeah, you have to, because now that's a finite element question. You have to. That's a good question. Because a lot of you don't actually. If you don't, you have to put a node here. If you don't put a node here, then the software is not going to understand. See, the computers are not smart, right? So the software is not going to understand that this column is carrying the beam. So what's going to happen is that the beam, it's going to, exactly, that's going to just.
So you're going to define the distributed load for both sections?
Yeah, have to. We'll see that in a few minutes. So you have to, that's why I said you need a node at each point, at each intersection. That's why I put a node here. I can't just have one beam, because it's not going to see that the column and beam are connected together. So that's an important question. That's the frame, how it looks like, and then there's nothing else we need to draw. So we're done with this. We don't want to select anything, we just want to assign. So here the assignment, we need to assign, the first thing we see is the joint. We need to assign joint restraints. So click on joint restraints, we have a hinge. This node is a hinge. So I'm going to assign a hinge. That's a joint restraint, and then we can go back and assign joint restraint. And then the one on the left is a fixed. So I click on the fixed one and click apply. You'll see it looks fixed. Right? So that's just to assign for support conditions. So I assign support conditions. I can show you something here that actually explains what I did earlier. That you can see something called local axes for frames. You see all the arrows, the red arrows are either pointing up or to the right. That's because I drew it this way. That's answered, So I mean, So we did the joints. Now these, we call that the boundary conditions, the bonds, the support conditions.
For where the beam and the column connect, you not put a connection there?
I will, yeah.
You will?
Yeah,
Okay,
but
sorry.
first I go with the order, right? Assign, the first thing it says assign joint. That's the next step. That's what I'm gonna put.
Right.
So the joint has to do with the support conditions.
Okay.
So I did the support
Okay.
conditions. And then now I have a pin here and a pin here, right?
Okay.
So I'm gonna assign that, choose assign frames. So now, so any other questions? It just needs practice. This becomes so easy after you do it 1 or 2 times. So the second thing is assign, is assign frame sections. So there are many things we're gonna deal with. The connections is one, but we will go with the order Sap wants us to go, so we don't miss anything. So joints, we don't need anything else from joints here. We don't care. We don't have springs. We don't have banded zones. We don't have anything. So that's something banded zones and this stuff we talk about in steel too, not here. So we go to frame. We need to assign frame sections. So we go to frame sections. You see, it gives you the sections you already defined. So we have here a W 14 by 109. So I go to the W 14 by 109. Let me get this out of the way so it doesn't confuse you. So we have a W 14 by 109. We select this member. That's the 14 by 109. Go to the 109, click apply. See, it gives you 14 by 109. And then the beam, it assigned everything, as you can see, Sap assigned everything as the first section you assigned. So you need to change that. And then the beam, we have 2 beam elements, right? We said we have to have 2 beam elements. Otherwise, Sap will not understand that there's a connection. So we need to select these two and click on the W21 by 44. That's it. And this one is already assigned as a 14 by 99. So we're good. So we assign the sections. Now we need to assign, go with the order. We don't need any property modifier. We don't need any overrides. Now that's important here, releases and partial fixity. That is the answer to your question for connections. So that's what we want to do. Let me get rid of that first before we go, so let's don't confuse you. So we go to releases, partial, partial releases and fixities and this stuff, that's, we have a pen here, right? There's a pen here, and there is also a pen here. That's bent, and that's bent. So, now that's something has to do with how SAP, that's something has to do with SAP. Has nothing to do with me. That's how SAP defines things. You see this red arrow? We call these arrows local axes. These have to do with the element itself. Each element has its own arrow. So we call that arrow 1. And then you see that's the red, the green one. The green one is going to be arrow 2. And you guys can see it, right? These two arrows.
Can you show us how you put those all together?
The arrows, yeah. Go here, you see this display thing, and then you click here, local axes at the frames, and click apply, and that's how it shows you.
He did like that.
Yeah. So, and it gives you many other options, but you can show something called extrude. If you look at 3D, you see the beams, you make sure the beams are and columns are put right, you see the eye-shaped beams, how they look like. Many other options you can do. But anyways, we're not doing extrude. So you see there is a red, green, and there is a blue arrow. Right, so I just want to show you what, the whole idea is to show you there is 1, 2, and then there is one out of plane, the blue, it's called 3. So if you cut a section, let's assume you're cutting a section in the beam. You'll see the beam is a W21 by 44, and then you'll see the arrow 3 will be in this direction, right? That's what you'll see, right? So what it means now is that 3 is the x-axis. So when you're dealing with moment about x, that's the M3. We call that, SAP calls it M33. So just the axis, 3 is the x-axis. That's the whole idea. So now when we want to release, when we put a pin, that means that we don't have a moment. We're releasing the moment, right? So we're releasing the moment. You see there is moment about 2, moment about 3. We're releasing the moment about 3. That's measured axis. Even SAP calls it measured. That's the MX. So for this beam, we want to release the moment at the start node. So I just select here start, and it's pinned. I put a number only if it's semi-rigid, if it gets some stiffness, but it doesn't because it's pinned. So I keep it as default, and I click apply. You'll see draws a pin here at the start node. So it's a start one. And then I do, so that takes care of this pin. The other pin is at this column, and you have, that's axis 1, so that's at the end node of the right column. So I select the right column, and I need to release the moment or apply a pin at the top, so that's the end node. So I have to unselect the start and select the end, and click apply, and you'll see we go it right. So it looks right. So That's how you put your pins. When you know, so now it understands there is a pin. You shouldn't have a moment at the pin, and it's about. And M33 comes from axis 3, which is the blue one. That's out of play. So there's an out of play axis.
Question.
Yep.
So we release the bottom column instead of doing the ends of the top? Because that, is the top column like one continuous beam, but we just had to draw it in SAP as two different ones?
So the top, you're talking about this column here?
I'm sorry, the top beam, that is a
Yeah.
continuous beam.
That's
all the way
continuous,
across.
yeah. It's not released, right? Because I showed you, you remember last class I showed you the connection? Showed you the beam is continuous like that. You know, you have a column here, and then this column, the beam is continuous, and then the pin is in the column, right? The beam is continuous. So that's, yeah. So that's why you don't, the pin, I mean, if I want to be too accurate, I should draw the pin like that. You know, it's, you have like, that's why some textbook will do it, draw it like that, where it shows that the pin is in the column, something, because if it's in the beam, then it becomes unstable. You can't put it in the beam here, because the cantilever is gonna fall, right? And you can't have a pin here. So that's it, that's all what, so we follow the same, you know, order. We did everything, we don't have anything else to worry about here. Now we need to apply loads. So that's, so we're gonna deal with frame and joint loads now. To apply these loads we have different loads. So what I did is just now I drew the frame, let's save it. And we haven't applied any loads yet. So any other questions?
So if the connection on the left between the top beam and that first column,
Yeah.
say if that wasn't the shear,
Yeah.
where that top beam goes into that, maybe it laid on top, would you, and it was pinned in the same, you would just pin that other
Yeah,
one?
then I would pin the column, yeah, same way. Yeah. That's why, you know, you see I put here, like, that's why in steel design we have to show where the pin is at. You just don't put it anywhere, yeah. Because it depends on how you connect it. So yeah, that's how it looks like, and then now we need to apply loads. So before we apply loads, you guys get this like so far?
Yeah.
And understand what's going on. I mean, even if you can't do it now, I mean, it takes longer to do it first time. If you can do it now, at least you understand what I did. You know, like you can go back home and do it. So we need to apply loads. So now we look at these load diagrams. A lot of loads here we have. So I'm gonna go look at joint loads. Joint loads are point loads, pretty much. So now I got a problem here that I didn't account for, but it can be solved with, you know, no one answer to these loads because, yeah. All right, let me see how. Right. We have two options. You see, we got some loads. We got some loads on the nodes, right? One of them is on the frame. So you have one option now. You can still assign these point loads on the frame, not on the nodes. Makes it kind of complicated. Or you can add an additional node. That's something you can do after, even after you draw your section or your frame. We can add another node here, N6. So it takes care of this point load. You can do something like that. So there are many ways to do it, by the way. The easiest way to do it is that we select this beam, divide it into two beams. So we go, if you go to edit, that's why we have the edit option. And then it says edit lines, and there's a divide frame option. Go to divide frame, it already gives you the number of frames. I need 2 frames. And then the ratio is 1, so there are 2 equal frames. problems. And you click apply, gives you a node in the middle. So solves the problem. So that now these are two separate beams. And you can go back, you see you have this option that shows you, shows you the sections, releases, local exceeds, everything you need, so it still works. So now I put a node, I split, I mean, that doesn't affect anything. It just makes it easier for me to apply point loads. You don't have to go that option because there's another option here where you can apply frame point loads, but you have to measure distances, becomes complicated. It's just easier to select joints. But anyways, that's do. We are applying forces. So I click apply forces. We have a dead load. So we have dead loads. We have the option, see the joints option here is invisible joints. We can unselect that and click apply to start see the joints. Makes it easier to select them. So now I have a dead load. I have, see now I'm on the load pattern dead. If you click, you see the list of loads we assigned. Dead, live, earthquake, snow, wind, all of them. So I have point loads now. I need to apply dead loads. I need to apply the 120. So I have two dead loads at these two nodes of 120. And they're in the Z direction and they're negative. So I put, and make sure I'm using kips. So the kips here still, I'm not using pounds. Because otherwise, you know, be using the wrong units. So that's 120. That's that. Make sure you're under the right load pattern. See, I put it wrong. See, that's the good thing about SAP. You know, you have to put a negative sign because it's, you know, you have to select it one more time. You only need to select this frame and replace existing loads with a negative 120. See, it gives you the arrow. See, that's stuff you get into. You know, so the other two nodes are 70. So I put here a 70 and kips. We add that to the dead load and make sure it skips here. So I'll take the point loads first, get rid of all point loads for dead, live, and wind, and everything. So if you look at, that's dead. I have to do this change, I have to go to live now. So live load, I have different loads. I have a 90 kips and 45, so that these two will be 90 in live load. So now I'm under the live load and minus 90, and then I need 45 in here. That's live load. That's the point load. So far I haven't done it yet, the distributed load. It's all live and it's in the negative Z direction. It's all gravity loads. Then I need to put the point loads for snow and wind, for wind and earthquake. So I go to the wind option. I have a point load in this direction. Put 0 here, because I mean, and put in the X direction. I need 150 kips. So apply 150 for wind. Make sure it's the right one. And then you do the same thing for the earthquake. It's 200 kips in the earthquake. That's all the point loads I have. The rest is distributed. So I just did all the loads. You can check it one more time. There is a display option, but we will go to that after we do the distributed load. So make sure all of them are correct. So let's assign now. We assigned all the joint loads we have. We can assign now frame loads. We have gravity forces. I don't like to use the gravity one. I'll go to the distributed. It's the same, it gives you the same answer, but gravity is more confusing to deal with. So I go to the distributed load. But you can do the gravity, it's just, you know, have to do a lot of changes. So that load, that's the first thing. Gravity, so that means in the negative direction, negative Z, and it's force, and I have a uniform load. So that load, I have to select all these beams and apply a uniform load. It already defines it as gravity, so I don't have to put a negative sign. That's why I like this option. But I mean, you have distributed load in X, Y, Z, and so on, but I'm really, usually uniform loads are distributed in gravity. So that's 3 kip foot. So make sure you see it tells you it's kip foot because I already assigned kip foot. If I change that to kip inch, then it's going to be kip inch. Then you have to divide by 12. So click apply. You see the distributed load for battery, and then you have distributed load for live. So same thing. Go to the live option, and that's 2.5. That's 2. Click apply. And you can see it says frame distributed loads live, and then it shows the 2. So make sure everything is correct. And then we have the snow load as well, and that's 2.5. And that's it, that's all the loads we have. So if you go to display, and there's an option here to show assigned loads. You go to assigned loads on frames. You click here, let me get rid of the sections and local exceeds and releases here so it doesn't affect us. So you see that loads, that's right, yeah, let's also get rid of I think there's something, yeah. So it gives you the dead load, and then you can show live load, looks right, and snow, and then wind, and then earthquake. So all the loads are.
What are you clicking on right there?
Wind. So that's earthquake. So that's 200.
I'm saying like where were you making that click?
Oh, this.
Oh, the arrows down the bottom. Gotcha.
That's the change, between these. So I mean, we're done now. There's nothing else we need to. There's nothing else we need to do. That's we applied all the loads. There's one important. So we're done with the assign part. There's nothing else we need to assign. Assigned everything. We need to analyze, and we need to something called set analysis option. We need to click that and see what that is. We need to make sure we assign, by default, SAP assumes it's a 3D frame. So if you keep it as it is, SAP will not understand that we are making simplified analysis for 2D analysis, and then the frame is going to fall, in this direction. It's going to turn out of plane. So we're not doing 3D. So you have to make sure, otherwise it's not going to work if you don't do this step, because SAP doesn't understand, it's 2D. It's going to assume it's going to go, it's weak and out of plane. So we have to make sure, click X3, and you see it come by default. Then analyze, we can run the analysis now. Let's see if that will work. We run it. So, see, that's the deformed shape. That's how the frame will, deform. And you can see there is a deflection here in the middle. So that's how it's gonna deflect and live load. And you can also, animate it too. So that's very important, actually, what I did here. Because it shows you here there is a pin. See this 90-degree angle? It's not there anymore. So it shows that there is a pin. Same thing here, this is not 90-degree anymore. So that shows you that we did everything right. So that's that. You see that's live. Snow. You see snow, we didn't have a point load here, so that's why in snow you see this thing is not like really, it's sagging, beam is sagging here. And then you see the horizontal ones, that's earthquake, that's wind. So you see that's a fixed, this is acting like a cantilever. See that's fixed, so 90-degree angle, there's no rotation. This one is rotating. So you see it also can move too. And wind and earthquake would look the same. So that's the first thing SAP gives you, the deformed shape, how the shape will deform. And you can get it from here as well. You see here it says, or you can go to display, show deformed shape, and then you can apply for bed, live, and earthquake, and all this stuff. So that's the first thing we need to do. The second thing we need to do is we need to look at the shear and moment diagrams. So we go to display and show forces, stresses option, and then it shows here we don't need the joints, or actually we can see the joints if we want to see the reaction forces, but we're interested more in the frame cables diagrams. So here it shows many options. You have dead load, you have all the list of loads you have, and if you click apply dead load, we selected axial force. So that's the axial force. It gives it, we can have it as a show values instead of a fill diagram. So you see you got 146. If you do the analysis, you'll end up with the same answer. So we got one compression. See, we have compression here because of dead load. So that's the dead load option. We got compression here, 146.25 kips. And then compression in the other column of 323 kips, 24, and that's kips. And you can see the shear diagram too. That's based on dead load. So you see the shear diagram looks familiar, right? That's how a shear diagram looks like. It's just the sign convention is different than what you guys are used to in analysis, structures 1. And then the moment, so shear is shear 2, because that's the local axis. Shear is shear in the y direction because that's axis 2, so that's the y. So we're talking about shear in y direction. And then we're interested in the moment in 3, M33. Click apply, you see the bending moment diagram. So I got almost 700 kip-foot moment. That's very high, and a negative moment here. And SAP draws the moment on the tension side. So that's not what you guys are used to in structures 1. That's the opposite of what you do in structures 1. And that's what I do as well. Like you'll see in this class, I'll be always doing the tension side. Because I can understand where the moment is at. So here, this means that the moment here is positive tension at the bottom, compression at the top. So that's why the moment is at the bottom. And here it's tension at the top, compression at the bottom. That's why it's negative. So we can see all these diagrams, moment, shear, and like you can see for live as well. That's the moment diagram for live. That's wind. That's the moment diagram for wind. And axial, we can check axial. There's some axial as well. It's 0. Yes, there's no axial. We can see shear at wind as well, 150. So this column took all the shear force coming from wind, the 150. Same with the earthquake. You'll see this column is taking care of the whole thing. And that's the moment diagram, how it looks like for ladder loads. So that's just doing structural analysis. We haven't done anything new so far. That's analysis, structures 1. So now we need to do the load combinations. We need to know how to do load combinations and put that, in like being able to put that in Excel, or find what to design for. So these are the loads, the structure we see: dead, live, snow, wind, and earthquake. So let's assume we're trying to design. We're trying to design this element right here. So we're interested about this column. Let's see what force should I design for. So if anybody was able to do the SAP analysis, do this, so it's, no one was able to finish. So now we need to design, right? The whole idea of doing this analysis is to design. So we did that, we already did the analysis. We want to design, so let's start. We need to see AB. So we have our frame. It looks like that. That's A, B. Then we have C, D, E. So we need to look at the question here is to determine the controlling load combinations for LRFD for beam column AB. So AB, we call AB a beam column because it's a beam and a column at the same time. We will see, I showed you the SAP analysis. We had axial forces P, we had a moment on this column, and we had a shear force, right? These columns were carrying all these loads together. So that's why we call it a beam column, because it got shear and moment and it got axial as well. So we call it a beam column. If you look at the beam, BCE, call that a beam because it doesn't have any axial, it has only M and V. It has shear and moment only. There is no axial, there's no axial effect. So it's completely different designs, by the way. We'll not cover beam columns completely in steel one, we talk about in steel two. And then CD is a column or a compression member. Because it only has axial, there is no shear or bending. So the three different designs here we need to deal with. We have one member that got all three together, axial, shear, and moment. And then we got another member that has shear and moment only. And then we had a third member that got axial only. So we'll deal with the easiest one. Start with the easy one, right? When we try to solve, let's deal with the column first. Let's see this column. CD. So as you guys know, this column usually we create a table, for the column to put the forces in it. So that's column CD, and we put here that we have an axial force P in kips, and then we don't have a moment, so moment is 0, shear is 0, so we don't have to worry about. And usually we try to tabulate our results. So what I'm doing now, actually SAP can do it for us, but I want to show you how it's done. So some of you know that SAP can do it. It takes a lot of time, but we have to learn how to do it before we let SAP do it. So so we have these, we have a column, we have the force in it, and we want to know what's the axial force in dead, live, snow, wind, and earthquake. Put a table, create a table like that, and look at the axial force for each load case. So we call these load cases. So that this table is for load cases, and then create another one for load combinations. So we go to the SAP model, and then we look at the axial forces for each case. So click apply. We're talking about this column here. So it's negative. You want to be careful with the units too. So it's negative dead, negative 323.75 kips. You put these in a table format. Live is a negative 228.75. if you guys can't see it, I know it's, you have this option, you can see there's a display, there's an option here, and dimensions, tolerances, you can increase the font here, like I can double it. Maybe makes it easier for you, you guys can see it now. So we got P and live load. Did I put that right? That's, yeah, live and axial. Yeah. And then we have the snow, 46.88. And of course, all these are zeros. So we don't care about moment, because that's a column, right? There's no moment and shear in a column. If you look at the moment, it's going to be 0 at this column. So we don't care. So that's for, and then we look at wind. Wind is 0 axial. Earthquake is also 0 axial. That's no, yeah, that's wind and earthquake. Yeah.
You do get shear and moment in the columns when you have the lateral loads, though, right?
No, not this one. You got it. So
Oh, not that one, but the other one, right?
yeah, but yeah.
Because it has
So
the
that's
fixed
why
range.
we call it we call this one a beam column, because it's a fixed, it's fixed support, right? That's why. So that's why we're getting all the shear and moment in this one, but we're dealing with the CD spin pin top and bottom. So we call this column we call this one the leaning column, you know, in design. Call it leaning column. And this one we call it the non-leaning column. Because this one is responsible for the lateral resistance. Like if you take, this one is a burden, you know, this is like this column is leaning on the other one, it's not helping it, it's, you know, adding more forces to it. That's, yeah. So that's why there's no moments here, this is only axial. Even with lateral loads, you don't get any moment. So here we have 0 wind and 0 so we create this table for load, we call that the load cases table. Now these are service loads, that's why I put the P, and I can call here that's service. That's the loads the structure sees every day, all the time. These are not what I'm going to use for design. I'm going to do the load combinations for design. And we usually do that in Excel, but let me do it by hand once and then we use Excel. You know, next class we'll be using Excel to do the rest, because it's a lot of calculations. So we create another table called the load combinations, or load combos.